I know. All right. No, I'm not doing all of them. No. Okay. What's the value of the unknown delta H, the enthalpy of the energy diagram? Can you see this? Here's the liquid form. Here's the gaseous water. Think of these as the you can think of these as reactants. This is the products with the difference. This is just a new type of enthalpy diagram.
Delta H.
242, right. So you're pretty much just looking at the difference between this delta H, and here. I guess I should draw this delta H because you can't see me. This delta H, and here. Okay, so the difference is negative 242. Cool? It's just a different type of one. Alright, just learning how to read these. Okay, in a chemical reaction, the difference between potential energy of the products and potential energy of the reactants is defined as it's called delta H, but what's the terminology we use for that? Heat of reaction, thank you. So be able to transfer between what I mean by delta H, enthalpy, and heat of reaction. It's called like 3 or 4 different things. So make sure you know that that's the same thing. So when you see it on a graph, though, where's delta H? Which of these? 4. So you're talking about the difference in energy between the products and the reactants. So from here to here is delta H. What is number 1? From here to here. What's that called? That's activation energy. And that's pretty much the only one that we need, other one we need to know. Well, what's number 6? Trick question.
Nothing.
It's also activation energy. This is the activation energy for the forward reaction from here to here. This is the activation energy for the reverse reaction because it's going backwards. So we'll get into kinetics actually next meeting. All right, bond breaking. So this is a review from yesterday. Okay, why? Karate chop it. Right, okay. So know that it's always endothermic. We're going to use like positive numbers for the bond breaking process and negative numbers for the bond forming processes. Just a minute, we get to actually forming and calculating these. So it's going to cause us to put in energy because the bond is very stable and the arrangement of electrons. So like it's a covalent bond, the electrons are between the two atoms. So to force it apart, you have to put energy into that process. So know that bond forming. Next up, why? Read that. This is just a quick review. This is like the last, so we learned how to do Hess's law with delta H's and using like heat of products minus heat of reactants. We used to do Hess's law with all the different reactions and flipping and manipulating the things that we need to. This is the last type of Hess's law with bond association energy, so we just got to know about how to break bonds and how to form bonds first. Most stable is once we form bonds, it's going to be a happy place. Okay, the energy is going to be released because that pent up energy is not useful for the system anymore. We'd rather give it to the universe. The universe wants all the energy. Okay, and there's my little picture to show you that. Okay, this I found this online. I thought it was super cute. So it's more favorable to be married. So nitrogen molecules together, happy, and memento. And that's an endothermic. Well, as you break it, it's an endothermic process. You have to put energy into breaking them up for nitrogen molecules. And then it is. Then the bond formation, they're unhappy. Whenever we put them back together, they're bonded. That's an exothermic process when we putting out that pent up energy. Okay, isn't it kind of cute? Right, come on, Bryce. Okay, so bond association energy. We know that we have to use energy to break a bond. We know that we release energy when we form a bond. How do we actually put that in a formula? Really easily, like this. This looks really similar to what? Hess's law, but the bit that's different is the reactants are first and the products are second. But I don't like to write it as bond association energy of the reactants and bond association energy of the products. I like to say bond association or bonds broken or bonds formed if they're in the reactants. Broken. So bonds broken minus bonds formed. And the way that you can remember this is that every single time we write one of these like little delta H of reaction things out, all it is just alphabetical order. So when we did delta H of reaction for Hess's law, we did H of products minus H of reactants. So P comes before R in the alphabet. Same thing here, but we're doing broken minus formed. Yeah.
What if the bonds aren't broken in reactants? Saying product side, or is it like it's bonds broken minus bonds formed, and it says reactants and products? Are they always going to be the same thing?
Yeah, because you have to, in order to form products, these reactants are different arrangements. You got to break them up so that you can rearrange those atoms to form your new products. So in a reactant, you have to break those bonds to get those atoms to separate.
So it's extra.
No, breaking bonds is endo. Right, correct, Sean. So this bonds broken number is always going to be a positive number, and the bonds formed, which is exothermic, is always going to be a negative number. Okay, so heat of reactions for these, it depends on how negative this is, but it can be positive or negative overall. All right, what page is this? 5 or 410? 410 in the textbook. All right, so we're going to do a couple practice ones, and then I'll let you guys do your problem sets with that at the end of class. Can I go next page? Yeah? Okay. So for this reaction, what's the name of that first guy? Ethene, good job. All right, so this is ethene added to hydrogen gas yields what? That's ethene. What is this? Huh?
Yeah, there's C2.
Ethane. So this is you're adding those H's back where the double bond was. You're adding them back so that, let's draw it out now. Because on these types of problems, you actually literally have to draw it out, count up the bonds you're breaking, and then see what energy is associated with that. So if you're looking in your textbook, you'll see that every type of bond has a different type of energy or a different amount of energy associated with it. So we'll use those in just a second. So when you're drawing this out, this is what this should look like, yeah? Because F, it's your double bond between your C's, and there's 2 H's on this one, 2 H's on that one. What does hydrogen gas look like? H bonded to H. You guys are so helpful this morning. No lone pairs because hydrogen can only handle 2 electrons at a time. How many does each of these hydrogens donate to the bond? 1 each to make 2 there total. Each hydrogen only has 1 electron, so it's cool, so there's 2 there. All right, yields. What's this one look like? Huh? C, C, H, 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 H. All right, questions on how we got this far so far? Yeah. Huh? Because it doesn't, because this cannot have a double bond. That H looks horrendous. This cannot have a double bond over here because each carbon can only have 4 bonds. So if you put a double bond between there, then it would have 1, 2, 3, 4, 5. It can't have 5. Yeah. Why did I draw it? Because I have to see the bonds that I'm breaking and forming. So I'll show you why. So how many C double bonds are over here? 1. Okay. How many CH bonds are over here? 4. So 1, 2, 3, 4. 4 CH bonds. How many HH bonds? HH bonds right here. So pretty much I've checked off the C double bond right here. I've checked off this one, this one, this one, and this one. And then I need to account for this one. So there's 1 H bond. Okay? Right here. That one. Okay, what are the numbers that are associated with these? Look in your book for C double bond.
611 kilojoules.
I believe you. Okay, 611 kilojoules per mole. I'm not going to write the units. I'm going to leave that one unit right there, and I will write the rest. What's the CH bond? 414. Is everyone seeing where we're getting these numbers? Oh, I'm sorry.
Okay, that's fine.
No, sorry. I just was looking down. All right, and then 1 HH. 436. Okay, so what's the total for the bonds broken? I have this down for us. Someplace. Some big number. Someone has their calculator. What is it? 1461 kilojoules per mole. Okay, now let's do bonds formed. We have how many CC bonds? 1. Right. Thanks. I'm gonna rewrite this. Put it here. C to C. How much is it? And then how many CH bonds? 6C bond to H. So that allows us to count for every single bond here. Done. This one was 6 times 4, 14. Sum that. Thanks, Alyssa. Well, I got this.
24.
Oh gosh.
7.
I like this math
28.
thing. I like it.
No, 24, 8 something. That's my guess. No, 24, 9 something.
It is 2831.
Peace.
Okay,
28.
kilojoules per mole. Okay, so what's the formula? Yeah.
I have a question.
Yeah.
For that one, you have to multiply before the other one.
Yeah.
So the actual number is 2, 7.
Oh. Okay. I have my notes over there. They're hidden away. So I'm just gonna read double check. 611 plus 4 times 414 plus 436. That is 2703. Is that what you said? Okay. So the bond's broken minus the bond's formed. The last step for us is just to subtract. So this is bonds broken minus bonds formed, which will be 2703 minus 2831. And that is that minus that negative 128 kilojoules per mole. Well, and actually the moles have already canceled, so I'm not going to write the moles because whenever we did this whole multiplication process, we're doing it per bond, so we're essentially per mole if you equate with the Avogadro's number. So this is the number, this is the delta H of reaction. We are done. Those are kind of fun because you get to draw pretty pictures and calculate everything we're good at, right?
You think it's fun? Yeah, start adding.
Okay. So this is now the delta H of reaction, and you could use this in another example later on. Yeah. Page 14 in your book. Yep. And they'll always be given to you in a big chart on your AP exam, so you don't have to memorize these numbers. Okay. All right. So that's it for bond association energy. Leah, let's do entropy. Yay! Entropy. And you have your thermodynamic, or you have your reference sheet out, right? Yeah, it's got some equations on it that are going to be useful for us. Huh? You will not even need your books right now. Okay. Say yes, we remember this law.
No.
Do you remember this?
Yep.
Okay, we with this? Okay. Know that whenever the energy for the entire universe is going to be conserved. The universe is everything. It's the chemicals, the surroundings, the coffee cups, the water, the air, everything. So whatever we have lost from the system or gained by the system will be given or taken away from the surroundings, just opposite in sign. So this is essentially allowing us to write Q the system if the system is losing something, and Q the surroundings. Okay, that's how we've been doing this forever. Just want a quick reminder that we're talking about the universe as a whole that's not losing overall losing any energy. So in this case, we're talking about the thermo or the enthalpy aspect of a reaction. We're going to start talking about the entropy aspect here in a second. All right, do I need to go back? Well, you don't have to write down all of this. You've already written this down, so this is a quick reminder.
I'm ready.
All right, how do you get big E again? What's the formula for big E? Q plus work, and how do you get work?
Negative
Right. Okay, so you could actually go, if you had your work, most time we ignore the work because work's like a physics thing mainly, but we can always take our Q and equate it to E if it's constant pressure or constant volume. All right. Second law of thermodynamics we've also slightly talked about, but this is like, you need to write down the entropy aspect of the universe. But this is something very, very important. This drives pretty much all of our reactions in chemistry. So the entropy of the universe. What is entropy a measure of? It says it right there. Disorder. So the entropy of the universe wants to be increased, meaning that the system, the chemicals that we're working with on a daily basis, the system wants to get rid of its excess energy and excess disorder and give it back to the universe. The only reason we do that is because we want the system to become more stable. And for it to become more stable, it's going to be going to a more disordered state to give it to the universe. So there's like four ways to say this law, to say the second law of thermodynamics, but you can say the energy of the universe is increasing, always, always, always. You can say that the system is going to go to more disorder. You can say that the entropy of the universe is increasing. We're going to talk about spontaneity here in a second. We're going to do that. Well, we're going to do that. It's phrased differently, slightly differently. Okay, so whenever I say possible positional arrangements, what does a solid look like on the molecular scale? Okay, so you got your solid, they're all really closely packed together. Okay, they're all really close. That is very, very limited positional arrangements. They're locked in place sometimes. They are vibrating, but very limitedly. As we go from solid to liquid, the positional arrangements, there's multiple arrangements. They can be floating around. This particle number 1 right here, can be here, or it can be down here, or it can be over here. It has the freedom to move around, technically making it have more entropy because it's got more disorder inherently available. So that's our liquid. And as we go from liquid to gas, the gas particles are getting more disordered, right? They're everywhere. The gaseous state is the most disordered state. Yeah.
By system equals stable, does that mean for when entropy is increasing, or is that
Energy being heat.
or entropy?
Okay. When the system does go into disorder, it means that it is more stable. So it's because the energy is not pent up, there's less potential energy between the bonds or between the atoms. Okay, so positional entropy is a good way to talk about the state changes from solid, liquid to gas and how it's increasing in disorder, which is increasing in entropy. So inherently gases are obviously the greatest in entropy, or S, the greatest in S. All right, we're going to kind of talk about this as we talk about chemical reactions and we count up gas particles. Yeah.
So like the gas is more stable?
In terms of entropy, in terms of overall energy, yes. Because whenever they're really tightly packed, there's a high amount of potential energy, which is stored energy. When they're farther apart, there's less potential energy. There's multiple types of energy, so it's hard to just say energy. Okay? All right, so this is actually, I put this document online for you guys to look at because we get into some of the issues with what are you talking about? You're talking about systems, surroundings, or the universe. So take a minute and just read through what you need to there, and I'll explain some of it. I'll let you read it first. Just yaws. And then as you're reading, write down what the word spontaneous means, because that's one, like it's a definition that you just need to know. It's not that it happens immediately, it's that it happens without outside intervention. Write that down too. And this is all in chapter 16 in your book too, just FYI. Alright, I see a couple people writing. I'm going to start explaining some of this. So the rule for the second law of thermodynamics is that the entropy of the universe always has to be increasing, meaning it always has to be positive. So that's why we're seeing over here in this chart that the universe is always positive, positive, positive. So the way that's going to work out is either the system is increasing in entropy with this positive number, and the surroundings is also increasing, so overall there's all positive entropy, there's more disorder on all accounts, or it works out mathematically in these two, so that when we add them together, that the overall universe is still increasing. It's still positive. So normally you would never have to actually calculate the system versus the surroundings because we don't really care about the surroundings, we care about the system. So we're going to learn mainly how to only calculate the entropy for the system depending on the chemicals that are present. So we always want the entropy of the universe to be increasing, which is just following the second law of TD, or second law of thermodynamics. So that's mainly the goal of this chart, what it's trying to portray to you. Another thing we need to talk about is how do we calculate, and what are the units for this? Okay, that's kind of hard to see, but whenever you write out entropy, it's always in joules per Kelvin. So we actually have Kelvin present here, and this is how it's written in your textbook too. Okay, so when a system receives an amount of energy, Q, at a constant temperature, the entropy increase of the surroundings is equal to this right here. Surroundings equals negative Q over T. And so this is what this means, joules over, most of the time we put Celsius here, but in the book and in whenever we talk about entropy, it always uses Kelvin, because Kelvin is, we use Kelvin because it's important, because we have to talk about what absolute zero is. What's absolute zero?
0.
0K, when there's no motion, no movement, no kinetic energy, nothing. Okay, so we just need to know how to appropriately symbolize entropy and its units. Leo? All right, we're going to practice a couple of these. All right, oh, I gotta just third law. Okay, so there's 3 laws of thermodynamics. The last one is talking about a crystalline structure. The perfect crystalline structure has no hint of energy at all. So at absolute zero, the entropy is 0. And I have a picture to show you that too. So these are 3 laws that we probably just need to know, like, by memorization, so know how to recite them. So on the AP exam, they can give you a multiple choice question. It says, what is the third law of thermodynamics? Something easy as simple recall. And what's one here? The reason that we have to know this law is because we need a baseline. So whenever you have entropy, whenever delta S is equal to 0 for a perfect crystalline structure, this gives us a baseline. So everything other than a crystalline structure, a perfect crystalline structure, is going to have a higher amount of entropy, a higher amount of disorder. So that we set this equal to 0 so that everything else is higher. If you look in the back of your textbook in the appendix, like where you've been looking at your delta H's, you'll find all the delta S numbers, and they should all be positive. Okay? Okay, so here's your crystalline structure. At 0 degrees, or at 0 Kelvin, all of these are not moving. All these particles are sitting still, and they're in a arrangement where the things are attracted to one another. But its entropy, its disorder, is 0. As you start to increase the temperatures, the kinetic energy increases, and so the crystalline structure starts to vibrate more. There's a little bit more motion involved, and so it's going to have a higher amount of entropy. So the delta S will be positive here. Okie dokie? And then this is just another description or visualization of the same thing. This is not for solids, though. This is for whenever you take your solid and dissolve it in water, the entropy increases. So every single time, like in your lab yesterday, this might be good things to kind of jot down. The entropy increased for every single solution. So the enthalpy may have increased or decreased. The enthalpy was your Q, but your entropy, every single time, it went from solid, nice structured solid, to an aqueous solution. So that might be something to mention in your analysis, or if you're doing a lab report on that one, do that. Cool? All right, so we talked a little bit about how we went from solid, liquid to gas, and how the entropy actually is increasing, like the disorder is increasing. So when you're melting a solid, increasing S or decreasing S? Increasing S. So you're going from something ordered, and you're melting it to something liquid, which is going to be increasing entropy. Boiling a liquid, increasing S. Dissolving a solid, increasing S. So this is all increasing disorder. Raising the temperature of something, increasing S. So if you know that all of these are going to be increasing the amount of disorder, you're in good shape. Just being able to look at an equation or look at a scenario and tell me if the entropy is increasing or decreasing. If you can predict that very quickly, you can do the math part very quickly too. You just got to plug in information. So everything here is going to be temperature dependent. Yeah.
Was it always?
No, if I went from, well, for the universe, yes, but for the system, so this is all for the system. For the system, it depends. So I could go from liquid to solid, and the entropy would be decreasing because the liquid has more disorder than the solid does. Okay, this is what I wanted to get to. Sometimes I can give you an equation that has the states listed, solid, solid, gas. This one's gas, gas, gas. This one you say, oh, well, the entropy is the same. But it doesn't. It depends on the number of moles of the gas involved or produced or consumed. So in this one, obviously, we're going from solid to gas. This one gas aspect makes us have increased disorder, so an increase in entropy. This one down here, how many moles of gas do we start with? 3. So 1 plus 2. So it's 3. Okay. And then how many over here? 2. So we went from 3 moles of gas to 2 moles of gas. Less. So that one's going to be a decrease in entropy, so it's going to be a negative S. So most of the time it's pretty easy when it's solid to gas, but if you have to count up the moles, just remember if you're going from more moles of gas to less moles of gas, that's going to be a decrease in the disorder because there's less positional entropy. Yeah. Good?
Yeah.
Cool. We're almost done. We can go calculations. Yeah. I'm just letting people write down. Yeah.
What did you write down?
I was just talking about how whenever we went from, you can probably barely see that because I wrote that really sloppy. I was trying to squeeze my math in. Whenever we are going from gas to gas, you can't just look at it and say, oh, the entropy stays the same because the gases have the highest entropy. You have to count up the moles of gas, so that's 2 plus 1, which is 3 moles of gas. And then that's in the reactants, and then going to 2 moles of gas in the products means we're actually decreasing in the number of positional entropy arrangements. So it's going to be a negative delta S or negative S. Can I go? Yeah. Go. So the first law dealt with conservation of energy. The second law dealt with
The entropy of the universe is increasing.
always increasing. And the third law,
There's no structure in perfect zero.
okay, is zero entropy, which is our baseline. We're going to use the back of the book for the other ones. All right. You'll probably remember some of the, yeah, Cameron. Rarely do we talk about the universe in chemistry. We're only concerned about the system because the system is what we deal with. That's our chemicals. Okay. All right. This is all online, so I'm videoing this right now. So, okay. Whenever you're trying to calculate the reactions entropy change, there's numbers associated with it, and that's in your appendix. That's what I was saying. It's in the tables with the delta H's. There's delta S's, and there's delta G's. We're going to get to Gibbs in just a second. So just how we did delta H of the reaction, what's that little knot thing mean again? Huh? Well, it means standard, right? Standard conditions. What are standard conditions? Again, just as a reminder. 1 atmosphere, 25 degrees C, 1 molar. Good. So just like we did heat of reaction was heat of the products minus heat of the reactants, we're doing the same exact thing. So this is for Hess's law. We're doing the same exact thing for the entropy. Don't forget that these numbers right here, these n's, are the coefficients of the BCE. So same thing, you're going to pull these numbers out of the back of the book. So this is just, we already know how to do Hess's law up here. We're just implementing it, the same exact type of equations for a different, different characteristic of the system. So you have your book. I think it's A2, no, A8. I will find it for us. I will find it. It's 8, well, it starts on 45. It's in the back of the book. So we're going to use those when we start calculating. I'll do one example here in a minute. So just keep your book out. One thing I want you to add to this slide, though, is talking about favorability. So if the entropy of our products is higher, actually I won't pause it up, but higher, is higher than the heat of our, or the entropy of our reactants, which is a lower number, what kind of number we're going to get over here? Positive or negative? Positive. So a higher number minus a lower number will give us a positive number. That means we have a positive delta X. Is that favorable or unfavorable? That's favorable, okay? So whenever you have a positive delta S or positive S, that's going to be favored because the entropy is increasing or decreasing? Increasing, right. There's an increase in S, which is good. We want this stuff to get really disordered. So if your products have a higher entropy than your reactants, that means your reactants got more disordered, which is a good thing. Okay? If you have a lower number for the products minus a higher number for the reactants, you're going to get a negative X. That is unfavored, right? So that's unfavorable for the reaction and for the universe, because that means you're going from something something of high disorder to something of low disorder. We don't want that. We want to go to more disorder. So this would be a decrease in entropy, which is not likely going to allow the reaction to actually occur. So it would probably be a no reaction in this case. Can I go forward now? Almost, yeah.
So unfavorable means no reaction.
Maybe. Okay, so I'm gonna put maybe in R, no reaction, because it depends on the enthalpy aspect. So you may remember from honors chem learning about enthalpy, your delta H and your entropy, delta S, and how you can compare them. If they're both favored, then the reaction occurs. If they're both not favored, reaction will not occur. If they're one or the other, it depends. So we're going to use a formula called the Gibbs formula to calculate when it depends, because it's all temperature dependent. All right, and we talked about spontaneity. We said that it can occur without outside assistance, and I'll actually have a better, the AP language, the way, remember I told you to use Coulombic attractions and you get a 5 on your AP exam yesterday? If you use the word thermodynamically favored, which I have on, I think, the next slide, then you'll get a 5 on your exam. So they don't like to use the word spontaneous so much. We still do, because I know what it means. You should know what it means. It doesn't mean that it happens like super fast. So there's something called kinetics we're going to get into next unit. So it doesn't mean it's inherently fast or slow. It just means that it occurs without you putting some extra energy into it. It's just going to happen. It might happen over 100 years, or it might happen in a minute. There's no time aspect for the word spontaneity means. Okay, and then we kind of did this. I just literally talked about this, but here's what I mean. When the entropy of the system is increasing, that's good. When the system is exothermic, so this is an increase in entropy. Whenever you have this combination, then the reaction will be spontaneous. Okay, so it's really favorable for the disorder to increase and really favorable for the heat of reaction to be negative, so that you have a energy given off to the universe. So if both of those are present or occurring for a reaction, the reaction is going to be spontaneous. You don't have to put any extra energy for it to occur. If it's the opposite, then what would we say? Will not occur. It's not spontaneous. So we're going to make a chart here in a second with these. Hope you'll start writing on that chat. Today's kind of a heavy note day. Sorry, guys. Every now and then. I think it's a lot for the notes. Yep. For this unit. Next Monday.
Is it our multiple choice and free response, or is it an actual test?
Actual test. I know, everybody does. I do that like once in the morning.
Do we still have them then?
Yeah. We'll practice it. Like in class, multiple choice and free response. She's asking if the multiple choice and free response that giving you as practice is the test. It's not the test. It's just practice. Okay. This is the big slide. Okay.
The base.
The big slide. All right. So delta G, or G is Gibbs free energy. That's the last variable that we're talking about. So we talk about delta H, we talk about delta S, now we have to talk about delta G. Delta G is actually telling us if a reaction is spontaneous or not spontaneous, or endergonic or exergonic. It's like 3 words that say the exact same thing. I'll let you write down that first. I spelled that spontaneous. definitional information because the exergonic and endergonic I don't think is in your textbook in this chapter, and it's specifically listed in your new AP curriculum, so I want to make sure we're all well versed on that. Essentially, yes. It's just sometimes a little bit of extra verbiage goes with it. I'll scroll down in just a second. All right, so the Gibbs free energy, the delta G, the sign of it, so positive or negative, will tell us if the whole entire reaction is going to be spontaneous or going to be non-spontaneous. But the technical definition of free energy, energy is work. It's going to be energy to do work. So that's why I have up here available energy to do useful work, which will be moving something in a certain direction. That's kind of related to some physics aspects, but we're concerned about volume changes when we talk about work. So determined by Gibbs free energy. So if you have a negative number, that means the system decreases in free energy, because the definition of delta G, or Gibbs free energy, is available or energy to do work. But that's a good thing, because if the system is decreasing in free energy, where's that free energy going? To the universe. Okay, and that's a good thing, because the universe should always be increasing in energy. That's the definition, or that's the definition of the second law of thermodynamics. So this is a good thing for the universe, which is what we're essentially trying to satisfy. Okay. So the exergonic part just means, if you can think of exer as a negative thing, like it's exiting, then you'll remember that exergonic has a negative delta G. Okay, so it flows in a direction that lowers the free energy of the system, following the second law of thermodynamics. So exactly what I just said. This actually just has it in words here. Know that stuff. I'm going to jump down here to the positive one. So whenever delta G is positive, that means the system is increasing in free energy. Well, where do you think that free energy is being removed from? The universe. So that means the universe is decreasing in free energy. That is not a good thing. The universe needs to be always increasing in free energy, or just energy in general. So if the system is increasing, that means the universe is decreasing, so it's going to be non-spontaneous. So a positive number means endergonic is kind of like endothermic, you're adding it. So remember that the endergonic just means that the free energy of the system is increasing, but the universe is decreasing, so it's actually not a good thing for our reactions to actually occur. So these two things are just opposites. We'll get into equilibrium in like 2 units, but delta G, when it's equal to 0, neither the forward reaction or the reverse reaction is favored, so it's at a dynamic equilibrium. Dynamic equilibrium. So the forward reaction equals the reverse reaction, meaning that it's not going to be favored to go forward or backwards. It's just done. It's just going to go back and forth, and no net changes overall. And so I put a little star by that so that you actually have that. We'll get into rates next unit too. So a lot of this stuff is like theory-based and conceptual-based, like explanation-based. There are mathematical calculations with it, but there's a lot of stuff you have to tell the AP people so that they know that you know what you're talking about. Certain words to use. You guys okay? Like on a scale of 5 to 10, or 1 to 10, how is this in understanding? It's a 1. What's a 1 is like, what are we talking about? 10's like, got this. Getting it? Okay. Entropy makes people sleepy all the time. Okay. I see a couple people responding. Thank you. All right. You'll have some time to absorb it as you do your problem sets, because your problem set's going to make you practice what we're learning, but this is kind of like all of chapter 16 at one time. Not all of it, like half of it. Huh? The beginning stuff? Well, we're trying to we're pulling like 3 big variables, like big thermodynamic variables, into one equation in just a second. So I hope that I can pull some of the information together. Yeah. So like a reaction that goes forward. So you're going from A plus B to C plus D. This reaction, and going from C plus D to A plus B, so going in the reverse direction, they're occurring at the same rate, and so they're equally favorable, so we don't talk about it being either way. Alright, I told you I'll tell you the phrase thermodynamically favorable. This is pulled directly from the AP curricula, the new curricula. So read through that. You pretty much need to know that anytime I say spontaneous, what we actually mean is that it's thermodynamically favorable. So that's just the terminology that would be nice for me to see you using occasionally. Okay, so if you use the word spontaneous, I know we mean the same thing, but if it helps you remember that the entropy goes up and the enthalpy goes down, so it's exothermic, then write down the word thermodynamically favorable. Can be favorable. So word of the day. It's because whenever people write spontaneous on AP exam, they mean, oh, it was like fast, like Superman, okay? So they don't want people to use the word spontaneous because they think that you guys don't know what it means. But I think you guys will know what it means. Yeah.
If we say spontaneous, I think
they won't count. They said they won't count it wrong unless you use the term incorrectly.
If they bring this up as a hint, as in it's gonna be one of the questions.
Oh yeah, it's definitely gonna be one of the questions. Like it's going to be a free response question.
Was that good?
Stuff about thermodynamics. Yeah, you know thermodynamics. All right, this is the last. Well, do these last two equations are the last one. This one looks just like your delta H and your delta S. That's where you're gonna find these values.
All over this.
In the textbook, not on the reference sheet. Actually,
It's there.
double check and tell me, is that equation's on your reference sheet?
Yeah.
The delta S, the delta H, and the delta G?
Yeah.
Awesome. So they want you to know this, but they give you it on the reference sheet too, so you'll use it apparently a lot because if they're giving it to you, you will have to use it. So just like everything else is calculated, products minus reactants, what do the numbers mean? Coefficients. Are the n numbers of the coefficients, multiplying appropriately. The last equation is called the Gibbs equation, or Helmholtz equation, is this one right here. Bryce, is that one on there? Yeah, okay, good. So this one, we have to figure out if a reaction from calculations, if a reaction is going to be spontaneous or non-spontaneous. If the delta G is positive, is that spontaneous or non-spontaneous? Look back at your notes. Non. If it's negative, it's spontaneous, or also known as thermodynamically favored. Okay? So what you do is you take your enthalpy number minus the temperature at which this occurs. So everything is very temperature dependent. That's like the third time I've said that, so important to know. And then minus the product of the temperature times the entropy. A lot of words. I gotta get my tongue straight here. So these two things, the enthalpy and the entropy, can sometimes be opposing one another. So if they are opposing one another, if you have to tell me if something is spontaneous or non-spontaneous, you have to do this calculation. And if the G is positive, it ain't gonna occur. But if the G is negative, it will occur. Okay? So when those two things are opposing, and I have a chart on the next page to sum this up. If they're opposing one another, you have to calculate. You can't just look at it and say, yep, we're good. On this part right here. Okay, so if the reaction is endothermic, that's not favorable.
Well, yeah, is that why? Like, do those two equations mean the same?
What this one and this one?
One and one.
Well, there are two different ways to calculate the same variable. So essentially, kind of, yeah. So like this will tell you the G of reaction, and this one will tell you the G of the reaction. But you can only use this one if you have the back of the book or a table with all those values. If you have this other stuff, then you have to do this equation to get you the same variable. Yeah, you're right. It just depends on what kind of information you have available to you.
So we're gonna have to calculate like delta H.
Yep. Or it could be given to you in a It could give it to you on a free response question, or you will have to calculate this variable and this variable, and then use the temperature and minus them, and then you'll get your delta G. It just depends on what information you have. Yeah.
It's not temperature change this thing.
No, it's just the T at which it occurs. You okay, Alyssa? Yeah. What? Delta H is the same. There's three ways to get it. You can get it. What? You can get your delta H like delta H of products minus delta H of reactants by using the back of the book. You can do the bond association energy, which I just taught you like 20 minutes ago, by breaking those bonds and forming those bonds. Or you can do the Hess's law where you add up all the equations and you add up all their delta H's.
I thought delta H was Q
What's
equals
the
MCAT.
break? Oh.
That's
Delta H can equal Q. once you've divided by the moles present. H is present everywhere. Okay, it is like the Holy Ghost. Okay, it is everywhere. This is the final. This is, if you understand this table, then you understand Gibbs free energy. Negative. Use some more paper, honey. I'm sorry, you're an AP chemistry.
Paper over here.
I'm not. You can do what you want. You can take a picture of this. This sums up pretty much everything in one table. So, if delta H is negative, what is that? Endo or exo? Exo. Exo. If delta H is negative, it's exo. If delta S is positive, is that a good thing or a bad thing? Good, because we're increasing in what? Well, disorder, right? Do I need to move? We're getting more disordered. So if it's exothermic and it's disordered, then that's good, and it's going to occur. So it's going to be spontaneous, and the delta G is a negative number. I don't want to be in this picture.
If you're gonna keep writing on it, I'm also done.
Okay. Because just wait. Yeah, see, look at this, Megan. All right. If the delta H is endo, and the delta S is decreasing in disorder. This decreasing in disorder, down arrow disorder. Sorry, this was increasing in disorder. So it's decreasing disorder and it's endothermic. Neither of those things are favorable. The universe hates this reaction. It will not let it occur. Okay, so it's never, ever, ever going to be spontaneous. That would be a no reaction, right? And then if it's these two things are the ones that are opposing each other, and so you have to actually calculate the delta G in order to figure out if it's spontaneous.
That was that formula.
That's what you'll have to do this equation for. Delta G is equal to delta H minus T delta S. So that's why I say it's spontaneous at high temperatures versus low temperatures, but you'd still have to actually calculate with the temperature given to you. All right, I'll stop writing.
What about the last one?
Both of these are the same. Both of these are going to make you have to calculate that for it. I just watched them.
May or may not.
So that's where the first one, you've got your endo, and then your increasing disorder, they're opposing each other. And then the second one, you've got your exo, but you're decreasing in disorder, so they're opposing each other. Does this help sum up some of this? Be positive for me, people. Does this help at all? Yeah. Okay, some of us are not being negative Nancy's. Okay, and then we'll talk about that bottom part later. Okay, and we already did, no wait, we already did this. We're good there. I ignore this for now. And I already told you that, so I'm going to skip that. And, okay, this is just how to calculate the delta G thing, because I told you I'd do one example at least. Okay, so if I want you, work with me, people. If I want you to tell me the temperature at which something is spontaneous, the delta G has to be what? If it's spontaneous. It has to be a negative number. For it to be spontaneous, it has to be negative. That means it's giving free energy to the universe. Or the system is giving free energy to the universe. Okay. That was on the chart. So if I want you to tell me what temperature does this reaction have to occur for the delta G to be negative, for the reaction to be spontaneous, what you solve this is, I usually use inequalities, but I'll do it like this. I want the delta G to be less than 0, right? You need to be negative. So how do I solve for T? I kind of got it laid out over there, but I'm going to show you how to solve over here. How do you solve for T?
You have to divide.
You add it to the other side. Add the T divided by T.
Okay, I'm going to get rid of that negative, so I'll do this way first. So I'll do it Cameron's way, like she's telling me here. Oops, less than delta H. That's only because if you have a negative number and you divide by a negative number, what happens to your inequality? You flip it. Okay, this is like what, algebra 2? Okay. So I want to solve for T though. So now I'm gonna minus my delta G. So there's like 3 ways you guys can do this. Minus your delta G, minus your delta G. So you get T delta S is less than delta H minus delta G. How do you isolate T? divided by delta S. And this is the whole shebang over here divided by delta S. Okay, so T is less than whatever this number is. And you would have those numbers in a table or in a FRQ given to you. So that's how you solve for the temperature at which something should be spontaneous. If it's a negative number, you flip it. Yeah.
So, but inequality wouldn't give you a number, just give you what's.
Oh, it would. Yeah, you would say this would be a spontaneous at any temperature below 3,000 or 300 K. Yeah. So it's either high temperature or low temperature. So you just if it's greater or less than.
So we use.
In this one, yeah, you have to use Kelvin. I did not say that. The reason why we're using Kelvin, who knows why we're using Kelvin? What's S measured in?
Entropy.
What's enthalpy measured in?
K.
Joules per K, and H is measured in joules.
So joules cancel out.
So joules cancel out, leaving you at K. Kelvin. Take a deep breath.
What is Gibbs?
What's what? Gibbs is the energy, so it's measured in joules. Or kilojoules, depending. So, yeah, so like if you do this, joules minus Kelvin times joules over Kelvin, Kelvin and Kelvin cancel out, joules and joules, that means this is measured in joules. I hope that you at least wrote everything down because you can have something to reference when you do your problem sets. Yes?
This is all on the internet, right?
This is now on a video. What? I'm not. Do I need to solve one? Yeah, I've been recording the whole time. Do I need to solve one problem? You want me to solve one of these? I mean, I kind of showed you how to solve it.
You solve like one of everyone.
Let's see, like. All right, for the decomposition of mercury.
This question.
I will wait. Work with me. For the decomposition of mercury 2 oxide, H is that, S is that. What's the temperature range for which the reaction is spontaneous? So what does G have to be in terms of sign? Negative. So we have to have G equal negative. What are you doing?
I always see like my work, but I never see the question.
Oh, see, that's why you write down your givens, right? So
I do that, but I just need the wording of the question.
I got you. Do what you got to do to make yourself successful. No, not that.
What was that?
Okay, so those are our givens. We want to solve for delta G. If you see delta H, delta S, and hush. If you see delta H, delta S, and delta G, what formula do you have to use?
The one.
That one. Delta G. Okay. And those little S's, those little knots mean standard. Those are numbers that you find in your book. Okay, so I gave you all of these, but you could actually you may or may not have to calculate them in the problem. All right, so what do we want to solve for?
G.
No. T. We want to solve for T. We want G to be a negative number. So how am I going to fix this to show that G is a negative number?
We just did this.
We literally just did this.
Unless T is less than delta.
Okay, so we just rearranged this, but I'm going to show you again. G has to be less than the difference of this stuff over here. Because we want G to be a negative number, because that represents spontaneity. Or thermodynamically favored. So, once you rearrange this, so we can go back and look at our previous problem. You wrote this down right here. We did. T is less than delta G. I hope I'm writing this down right. Oh, delta H minus delta G. Oops. Delta H minus delta G over delta S. But there's something special. What do you notice between delta H and delta S?
Which number is there?
It's KJ.
KJ and J. Well, we need to go to one or the other. What do you guys want to go to?
Joules.
Let's go to joules. So how many joules is this? 9,800 joules. I mean 9,800 joules. Yeah, you know what I meant. Okay, so how about I'm gonna rearrange it slightly differently because I don't like that we have delta G right here because we don't actually know delta G, right? So I'm gonna rearrange it and actually plug in our numbers. I wanted to go ahead and use what we had, but we don't have the numbers there. So we don't have this, right? We need this to be probably 0 so that we can say it's less than 0. Okay, less than 0 is negative.
return 0.
Well, no, we want it to be less than 0. So I'm saying that this number, whatever this product is, whatever this difference is going to be greater than 0. Because all we want to know is the temperature range. We don't want a specific T. Yeah. Because spontaneous, it says for it to be spontaneous, you need delta G to equal a negative number. So if delta H is 90800 joules minus T, and then S is 108 joules per Kelvin, it allows, if we substitute 0 in for G, it allows us to actually complete the final calculation, because you can't do it with two variables in there. So this number right here, T, we have to solve for, right? Solve for it. So T times 108 joules per Kelvin. So add that over here, 108 joules per Kelvin. So then you get, huh? What, this one? No. T times 108 joules Kelvin per Kelvin is equal to 90,800 joules. Now you divide by 108 joules per Kelvin. Divide by 108 joules per Kelvin. This cancels out. T is, oh, I forgot my inequality. T is less than whatever that division gives us, which is, what is it? 40. So this will occur at any temperature above 840 Kelvin, which is really high. Well, it only asks for what temperature is present. What temperature range for this reaction is spontaneous? Yep, it doesn't matter as long as it's negative. Yeah.
If it actually define G also, we should just plug the T back into the original.
You could, yeah, but it would still give you 0. It would actually have to give you some other variables.
So then, if it said G was supposed to be non-spontaneous,
Then you would set it so it's a positive number.
or greater than 0.
All right, I'm gonna pause this video since we are hopefully done.